In this video, we'll be going through the Part 3 and 4 questions from the June 2023 Geometry Regents. 32. Cape Canaveral, Florida is where NASA launches rockets into space. As modeled in the diagram below, a person views the launch of a rocket from observation area A, 3,280 feet away from launch pad B. After launch, the rocket was sighted at C with an angle of elevation of 15 degrees. The rocket was later sighted at D with an angle of elevation of 31 degrees. Determine and state to the nearest foot the distance the rocket traveled between the two sightings C and D. So our ultimate goal here, and when we look at this picture, is to find the distance between D and C. The reason we can't jump to doing this is because that is not a side of a right triangle, and that means we won't be able to use right triangle trigonometry or SOHCAHTOA. So what I'm going to do is I'm going to use the right triangles here. If we look at triangle ACB, I'm going to call side CB Y. And if we look at triangle ADB, I'm going to call this whole entire side C. And hopefully when we look at this, you could see that X is equal to the difference between Z and Y. What I'm going to then do to make this easier to follow along is I'm going to separate these two triangles. So here's the triangle with the 15, 3,280, and Y. Then we have the bigger one. This is 31 degrees, also 3,280 feet, and Z. Now these are both right triangles, so I can use SOHCAHTOA to solve for Y and Z. In the small picture here, a smaller triangle, we have the tangent of 15 is Y over 3,280. When I cross multiply, I get Y equals 3,280 tangent of 15, and we'll put that in the calculator. Just a tip here, most of the time, these questions with these like double triangles are going to be tangent as opposed to sine or cosine. All right, so we have that measurement is 878.8733511741. Okay, I'm not going to round anything there. I'm going to leave it as is. And I'm going to basically repeat the process over here with the other triangle. And I will now put this one in the calculator. All right, I've copied all of those digits there. We're not asked to round Y or Z, just X. So I'm not rounding these. We only round our final answer. Basically, in a question, you only round once. All right, now we want to find to the nearest foot. So we said before that X is equal to Z minus Y. So in my calculator, I'm going to subtract Z and Y. And I'm going to round this to the nearest whole number. So 1,902 feet. A small can of soup is a right circular cylinder. It has a base diameter of 7 centimeters. I'm just going to note there before going on that means the radius is 3.5 centimeters and a height of 9. A large container is also a right circular cylinder with a base diameter of 9. Okay, again, meaning radius is 4.5 and height of 13 centimeters. Determine and state the volume of the small can and the volume of the large container to the nearest cubic centimeter. All right, so let's do our volume formula for a cylinder. You'd look at your reference sheet to get this. And I would organize this nicely, clearly show what volume represents the small can, which one clearly represents the large container. So our formula is pi r squared h. The radius is 3.5, the height is 9. And I'm going to put this in the calculator. And it asks us to round each one to the nearest cubic centimeter. So this one's going to be 346 cubic centimeters. And here's the large container. 4.5 for this radius, 13 for this height. And this one to the nearest cubic centimeter comes out to 827. Okay, now there's a second part to this question. It says, what is the minimum number of small cans that must be opened to fill the large container? So let's think about this for a second. If the volume of one can is 346, one can, I'll write it out this way, is 346 cubic centimeters. If it's two cans, that's 346, and another 346, that's 692. That's still not filling the new container or the large container. So let's do 346 plus 346 plus 346. That one's going to be 1,038. That is enough to fill the container. So there must be 3 cans must be opened. And if we explain that, we can just say because 1,038 cubic centimeters is greater than 827 cubic centimeters. 34, parallelogram math has these vertices, and we want to prove that it's a rhombus. It is up to you if you want to graph here. That's why it says the use of the axes below is optional. Okay. If you feel more comfortable looking at a picture, you feel like you're a visual learner, then definitely go ahead and graph. It's not like you're going to be short on time on the Regents. You have plenty of time. So I'm going to go ahead and do that here. So I have M is -7, -2. A is 0.4. T is 9.2. And H is 2, -4. One big tip for these problems is that it's not saying, is this a rhombus? It is saying, prove it's a rhombus. So our calculations need to work. If they don't work, that means we did something wrong. We plotted wrong, we put a number in a formula wrong or in the calculator wrong. So keep that in mind that it's not asking you, is it a rhombus? We know it has to be, we've just got to verify it. Well, a rhombus is basically a quadrilateral where all 4 sides are congruent. So what I'm going to do is I'm going to find the length of all 4 sides. The way I'm going to do that is with the distance formula. And I'm going to do that, like I said, for all 4 of the sides. So I'm just going to set up the formula first, and then I'll plug in the numbers. All right, for MA, the distance between the x values is 7. Distance between the y's is 6. If I type in what's inside that radical here, this is going to give me radical 85. I'm going to leave it like that. If I do AT, the difference between the x's is 9. The difference between the y's is 2. Just type in again for a second what's in the radical. You'll see I get radical 85. Okay, don't forget to put the radical back around it. TH, I'll be getting 7 and 6 again, and we already know that will be radical 85. And HM will be getting 9 and 2 again, so radical 85. If you got any inverses from what I got, if you got -9 and I got +9, that's okay. That just means you're subtracting in a different order, and that's perfectly fine when using the distance formula. So I'm going to say that math is a rhombus because all 4 sides are congruent. Now again, there's a second part to this question. Notice these questions have this extra part because these are the part 3 questions, so that means they're worth 4 points each. And we have to find the area of MATH. If I got to this part and I hadn't graphed previously, I would have said, okay, now I need to graph. Okay. I like to calculate area, every area problem that the Regents gives me on a coordinate plane the same exact way, whether it's a right triangle, a regular, any other triangle, a parallelogram, a different quadrilateral. I plot it, and I'm going to use this box it in method. Okay, so that basically means I'm going to draw a box. Yeah, let me fix that one here. Around the shape. And I'm going to use my highlighter here to just like color in just a little bit so that you could see what we're doing. We're kind of thinking of this as a shaded area problem. You're going to notice that the two triangles I just highlighted have the same measurements, and the top left and bottom right here have the same measurements. Okay, but even if you didn't, that's okay. I'll pretend I don't see that for a moment. All right, so if I find the area of the rectangle, okay, so I'm going to find now the area of the rectangle. Its measurements, if I go from here to here, that's 16 units. And if I go from here to here, top to bottom, that's 8. So the area is length times width, so 128. I'm going to now number each of these triangles. So area of triangle 1 is 1/2. Area of a triangle is 1/2 base times height. We can see that we have a side of 7 and a side of 6. So that's going to give me 21. The area of triangle 2, 1/2 of 9 times 2 is 9. We're going to do the same measurements over here. If I do area of triangle 3, 1/2 of 7 times 6 is 21. The area of triangle 4 is 1/2 of 9 times 2, or 9. So to find the area of math, so the area of math is going to be 128, the large box around it, and now subtract out all of those surrounding areas. So 128 minus 21 minus 9 minus 21 minus 9. And our answer here is going to be 68 square units as our total area of math. The final question here is a proof. The proofs on the Regents are generally quite challenging, and they very, very often incorporate different rules about quadrilaterals. Could be parallelograms, rectangles, rhombi, squares. I've seen a variety of them. But it does really help when doing a proof if you know your properties of quadrilaterals. All right, for 35, quadrilateral ABCD is given. AB and CD are congruent. AB and CD are parallel. Diagonal AC intersects EF at G. And we know DE is congruent to BF. We want to prove that G is the midpoint of EF. In order for that to be true, that means that EG has to be congruent to FG, right? If G is the midpoint of EF, those two pieces of that line segment must be congruent to one another. So that's going to be my goal, is to show those two segments are congruent, and then I'll ultimately be able to prove that G is the midpoint of EF. The way that I'm going to try and do that is I'm going to focus, I'm going to go with my highlighter for a second here, on these two triangles. And I'm going to see if I could prove those two triangles are congruent to one another. Often when this happens, there are different ways to go about this proof. So there's not necessarily one right solution here, but I'm just going to walk through one option here in this video. I'm going to get rid of my calculator here since we do not need that for a proof, and I'm going to start setting the proof up. Okay, so I'm going to make two columns. And one is going to be called statement, and one is going to be called reason. All right, the first thing we're going to do is we're going to write all of the given statements. We're going to make sure we don't accidentally leave one off. I choose to write them all in one step. So I'm going to just sit here and I'm going to copy all of those given statements over. And for the reason, I'm going to just write given. Very often when I would look at one of these problems, I would look at a keyword in the givens. Is it a quadrilateral? Is it a parallelogram? Is it a rectangle, rhombus? What shape is it? This one gives us a very general shape. It just says it's a quadrilateral. It has 4 sides. I would now look at the picture and say, can I show this as a parallelogram? Can I be more specific since the problem wasn't specific for me? And I can. I do actually know that this is going to be a parallelogram because we have a quadrilateral, where one pair of opposite sides are both congruent and parallel. So I'm going to write all that. So I'm going to say for statement 2 that ABCD is a parallelogram. My reason for this is going to be a quadrilateral where a pair of opposite sides are congruent and parallel is a parallelogram. Here's why this is helpful. Now I get to use any property of a parallelogram in this proof, and there's a bunch of them and definitely some that are applicable here. Let's go back to the picture. In a parallelogram, we know opposite sides are parallel, but we also know, so for instance, that AD and CB are parallel. But we might also know that parallel lines form congruent alternate interior angles. So what I'm going to do is I'm going to show these two opposite sides are parallel, and therefore these two angles that I'm marking off in pink here have to be congruent because they're alternate interior angles. It is a lot to write. You definitely need space for a proof. And remember what I said before, there's different ways to go about a proof. This is just the route I am taking. All right, so I'm going to say here that for line 3, AD is parallel to CB. And my reason is opposite sides of a parallelogram are parallel. And now I'm going to basically show those angles are congruent to each other. So for line 4, I'm going to identify them. So one looks like angle EAG. And the other, FCG. Are alternate interior angles. My reason is parallel lines cut by a transversal form alternate interior angles. Then I'm going to say they're congruent. I'm going to say angle EAG is congruent to angle FCG because alternate interior angles are congruent. Keep in mind, as you're writing, proofs are long. This is a 6-point proof, so there's going to be a good amount of work and writing that goes along with it. So all I did was show those angles are congruent. I'm going to go back to the picture for a moment. If you need to pause anything to copy it at some point, feel free. Okay, since we know that this is a parallelogram now, we know that opposite sides are also congruent. So I know that DA and CB have to be congruent. I'm just going to put brackets here to mark that. So I'm going to write that about that next in my proof. So this is actually line 6. DA is congruent to BC because opposite sides of a parallelogram are congruent. Here's why that helps us. if we take a look at this, we know that the big sides here, AD and CB, are congruent, and we already know about DE and BF being congruent. So I'm going to show this through a little bit of highlighting here. We know the big sides are congruent, and we know these little green sides are congruent. So imagine if we subtract those out, those have to be congruent to one another. So that would make AE and CF congruent segments. Okay, so we're going to say that AE and CF are congruent, and that's by the subtraction postulate. Okay, so AE is congruent to CF by the subtraction postulate. All right, I'm going to go back up to my diagram and just clean this up for a moment. Okay, so I'm going to erase some highlighting and some pieces that I don't necessarily need at the moment here. So I'm going to erase some of these parallel markings. And let's look at these triangles again. I know a side is congruent to a pair of corresponding sides and a pair of corresponding angles. And I can also add in these vertical angles in the middle here by G. So I'm going to say that angle EGA and angle FGC are vertical angles. And that's because intersecting lines form vertical angles. And then I'm going to say they're congruent. Remember, we don't want to just say what they are. We want to always say they're congruent, so we can mark them congruent in our diagram. All right, well, now we have enough to prove those triangles are congruent. So I'm going to say that triangle EGA is congruent to triangle FGC. And I'm going to go back to my diagram. And hopefully we can see here that this is angle, angle, side. Okay, so I'm going to write angle, angle, side is congruent to angle, angle, side. Once we have that, we know that any unmarked pieces in the picture are congruent. So I know that EG and FG are congruent by CPCTC. Remember we said in the beginning that that was our goal? Well, if those two pieces are congruent, then we can prove what we need to, that G is the midpoint of EF. And our reason behind that is if a point splits a segment into two congruent parts, it must be the midpoint of the segment. So now we have successfully shown that G is the midpoint of EF, and that concludes question 35.